Back to computer graphics and visualization subject. In that module 5 we are discussing module 5. Again in module 5 we are discussing curves, right? Already we are discussing Hermite curve, cubic spline curves, right? Now today we are going to discuss Bézier's spline curve, means Bézier curves, right? This plane approximation method was developed by the French engineer Pierre Bézier for use in the design of Renault automobiles, right? This means the curve name is the engineer name who has developed this curve, right? Bézier's planes have a number of properties that make them highly useful and convenient for curve and surface design, right? It has number of properties. Those properties we will see at the end, right? Those properties made these curves highly recommended for surface design, right? They are also easy to implement. Whatever properties are there, very easy to implement. For these reasons, Bézier's planes are widely available in various CAD systems, in general graphics packages, and in assorted drawing and painting packages. That's why it is very popular, because it has some properties which are very easy for implementation. That is the reason these type of curves are used in many computer graphics applications, CAD systems and drawing packages, all those things, right? Here in general, a Bézier curve section can be fitted to any number of control points. As I told, these whatever curves we are drawing here, we are drawing curve not from starting point to end point at a time. We are drawing curves by using control points. Those control points are non-collinear, right? Means there may be n number of control points. Then we will draw curves section wise. Means if we have 4 control points, we will first draw P0 to P1 control point, P0 to P1, then P1 to P2, then P2 to P3, then P3 to P4, like this. Means section wise curves will be drawn. While drawing these, we have to satisfy some boundary conditions, right? That may be first degree, second degree, right? Derivative functions, those may satisfy depending on what type of curve we are drawing, right? That's why number of control points depends on number of control points we have to draw those. Although some graphics packages limit the number of control points to 4. Again, the means how many control points we have to select for drawing a curve, that depends on the package. Most of the packages will limit the control points to 4. Means always you have to draw a curve using control points 4, right? The degree of the Bézier polynomial is determined by the number of control points. As I told, degree is depending on number of control points. Always degree is, if number of control points are n plus 1, degree is n, right? Points to be approximated and their relative positions. As with the interpolation planes, interpolation meaning already I have told in Hermite curve and cubic planes, right? Interpolation means part wise. We are drawing part wise, means control point wise, means first control point to second control point, second control point to third control point, like that. We are drawing a curve, entire curve, means from P1 P0 to Pn, till P0 to Pn anyway we have to draw, but we are not drawing directly P0 to Pn. We will draw section wise, right? So we can specify the Bézier curve path in the vicinity of the control points. Means we have to specify the Bézier curve path in the vicinity of the control points using a blending function. Here we are using a blending function which controls your curve. Means it takes care of all boundary conditions on whether it is following the proper path or not. That blending, that is called a blending function. The characterizing matrix of boundary conditions, everything will be taken care in this, so that because when you are drawing section wise, it may happen that next section may not follow your path, right? That may be the case when you are drawing curve P0 to Pn section wise. At that time you might have drawn first section, then you might have drawn second section properly, means those paths, the two sections are following the path, but it may happen that third section may not follow your path, right? Whether it is following that path or not, to check that one we have the blending functions, boundary conditions. We have to check those boundary conditions. If the boundary conditions are satisfied by the previous section and next section starting, previous section end point and next section starting point, the boundary conditions are satisfied by the previous section end point and next section starting point. If they satisfy the boundary conditions, first degree, second degree, third degree, whatever boundary conditions, then definitely you will tell that yes, they are following the path, right? If they don't satisfy the boundary conditions, then definitely you are not following the path. At that time you have to take different actions, right? This is what will be taken care by blending function, characterizing matrix and boundary conditions. Then for general Bezier curves with no restrictions on the number of control points, for general Bezier curves there are no restriction on the number of control points, the blending function specification is the most convenient representation. If there are no restrictions on control point, then blending function is most convenient representation, right? Then Bezier curve equations, what all equations we are using for the curves by using Bezier, right? We first consider the general case of n plus 1 control points, right? N plus 1, if there are n plus 1 control points denoted as pk, that is xk, yk, zk, that is 3D. If we are drawing a 3D curve, then xk, yk, zk with k varying from 0 to n, with k varying from 0 to n, that is number of points 0 to n, right? These coordinate points are blended to produce the following position vector. Means you have to blend, means you have to draw in such a way that they have to follow the path, right? These coordinate points are blended to produce the following positions vector p of u, that is a position vector, that is a point p, control point p, that is a p of u, which describes the path of an approximating Bezier polynomial, function between p0 to pn. Means that you have to, as I told, there is implicit and explicit curves, right? Implicit and explicit curves. Again, whenever you are drawing any curve, the curve may pass through all the control points, or some curves may not pass to some of the control points, they may go to nearly. Means control points, they may not be at exact control point, but they may approximately, the curve may be approximated towards those control points, right? Which describes those, means p of u, that is a vector, p of u will tell which describes the path of an approximating Bezier polynomial function between p0 to pn. Means from p0 to pn, whenever you are drawing section wise curves, p0 to p1, p1 to p2, p2 to p3 like this, then this p of u has to approximate that section of curve which has to follow the, means in a such a way that has to follow the path of the entire curve, that is p0 to pn, right? This is the meaning of this line. Then the equation, generalized equation for this is p of u, any point if you take, any control point if you take with respect to u, that is a parametric equation, summation k equal to 0 to n, p of k, means p of k is in the control point at position k is varying from 0 to n, then Bezier, that is Bezier kn of u, where u varies from 0 to 1, means that is parametric value, u will vary from 0 to 1. Then you substitute, you change u value from 0 to 1, then calculate p of u for all the control points. Means all the control points you can calculate just by varying the u value, you calculate the x, y value for all the control points till the end, like a section wise, right? The Bezier blending function bz n of ku are the Brechtian polynomials. These are Brechtian polynomials, means that is explained like this. Brechtian polynomial is nothing but Bezier n of u equal to c of nk u to the power k of 1 minus u to the power nk, right? That is, means Brechtian polynomial will be expressed like this. Then again, if you expand c of nk, again we have given c of nk is n factorial by k factorial into n minus k factorial, that is c of nk, that is n factorial by k factorial into n minus k factorial. Equation 22 represents a set of 3 parametric equations for the individual curve coordinates. Equation 22 represents set of 3 parametric equations for the individual curve coordinates. For every curve coordinate, it represents set of 3 parametric equations. Right? What are those parametric 3 equations? Those are, means you have to calculate value for x for every control point. For every control point, if it is a 3D curve, you have to calculate 3 values, that is x value, y value, z value for every control point, right? Just by varying u, you start calculating x, y, z. Means you take u equal to 0, then u equal to 0.1, then u equal to, means again that offset you decide, u equal to 0.1, 0.2. if you are taking e equal 0, then 0.2, then next 0.4, then next 0.6, 0.8, 1 like this. You can calculate just by varying u value for all the x, y, z if it is 3D. Right, that is k equal to 0, n, xk means x at a point, what point you are calculating k, Bezier, k n u, similarly y of u, then yk Bezier n, then z of u. In most cases, the Bezier curve is polynomial of a degree that is 1 less than designated number of control points. As I told, if there are n plus 1 control point, then degree is n. Degree is n. Any Bezier curve polynomial degree is always, if there are n plus 1 control points, then degree is n. For example, if you have 4 control points, if your Bezier curve, if you are drawing with the 4 control points, then degree of that polynomial is 3. Degree of that polynomial is 3. 3 points generates a parabola, 4 points cubic curve, and so forth. Right? 3 points generates a parabola, 4 points cubic curve, and so forth. Again, I have told why you have to prefer 4 or 5. Why you have to prefer 4 or 5? If you use less number of control points, then it is approximation becomes very difficult. Approximation becomes very difficult. If you use less, means less than 4, if you use control points, then approximation becomes very difficult. Again, if you use more than 4 or 5, then complexity will increase. Higher order polynomials, if you go as an higher order polynomials, then complexity of those polynomials will be increased. That's why most ideal control points are either 4 or 5. Right? Then here, by using 3 control points, one is by using 3 control point Bezier curve, that is P0, P1, P2. Right? That approximation is like this. Again, you draw P0 to P1, then satisfy the boundary conditions at P1, end of the P0 to P1, then at the starting of P1 to P2. Like that, these are the different Bezier curves drawn with 3, 4 points. 3 and 4 points. For figure demonstrate the appearance of some Bezier curves for various sections of control points in the xy plane z equal to 0. Right? As I told, again, advantage of Bezier curve is a local adjustment is possible in this case. Local adjustment is possible in this case. Right? Then here with certain control point placements, however, you obtain degenerate Bezier polynomial. With certain control point placements, however, we obtain degenerate Bezier polynomial. Means certain control point placements, if you change the control point positions, then you can degenerate Bezier. Means at that point only it will make effect. It will not affect the entire curve. Right? That is the advantage. One more advantage of this Bezier curve. For example, a Bezier curve generated with 3 collinear control points is a straight line. 3 collinear control points is a straight line. Means you have 3 points, but all are collinear. Means all are in only one line. All are collinear. At that time, we will get straight line segment. Right? And a set of control points that are at the same coordinate position produces a Bezier curve. Set of control points that are at the same coordinate position produces a Bezier curve, that is a single point. Means you have 3 points, but all are at the same point. All are at the same coordinate. Means you have 3 points at 10, 10, 10, 10, 10. That is simple point. That is a Bezier curve, simple point. You have 3 points, different points, but they are in a straight line. They are collinear. So at that time you will get a straight Bezier curve. That's why I have told at the beginning, non-collinear control points if you have, then you will get curves like this. These are all non-collinear, right? Because one control point is here, one is here, one is here, again here. One control point is here, but these two are linear. But if you combine all together, these are non-collinear. Right? Like this, if you have, you will get Bezier curve-like sections. Right? Recursive calculations can be used to obtain recursive binomial coefficient values as, means if you want, you can use the recursive functions C of n k equal to n minus k plus 1 by k, n minus k plus 1 by k into C of n k minus 1 for k greater than or equal to n greater than or equal to k. Right? Also the Bezier blending function satisfy the recursive relationship. Means again, one more advantage of this Bezier curve is you can go for recursive functions while you are drawing any complex curve. Right? This is the recursive Bezier blending function b of z n k of u equal to 1 minus u, Bezier of k n minus 1 of u plus u, Bezier of n k minus 1 n minus 1 u, where k varies from n to 1. Right? With Bezier this. Then for cubic, one example we will see by using these equations. For cubic Bezier curves order n, for cubic Bezier curve order n, right? Order is different and degree is different. A polynomial is 3. A polynomial is 3. Index I varies from 0, I equal to 0 to I equal to n, that is 3. I equal, that is 3, and u will vary from 0 to 1. U will vary from 0 to 1. Cubic Bezier curve blending functions are defined as cubic means this is a degree 3 order 4, right? That is, as I told, degree 3 means there are 4 control points. Degree 3 order 4 is then order will tell how many control points, right? Degree will tell power of that equation, right? That's why P of equal to, U equal to control point P naught B0 3 up U, B0 3 up U, means if you go this B0 3 up U, that is 1 minus U control point, then first control point, blending function, that is B0 raised to 3, means again there are different conventions they use. How they use, if you see here what they used, Bezier Kn they are used. In this we are using that point and n. Here we are using one is subscript, one is superscript, like that. There are different conventions they will use again, but concept is same, right? That is blending function at 0, degree 3, right? Because there are 4 control points. Up U plus P1 control point 1, blending function at 1, degree means 3, right? That is U. Then P2, that is n. Here n is degree, n is order, right? That is P0 to 3, means 0 to 3, that is order. Then P2, then 3, then P3, this. Then B0 of 3 you can express, that is the diagram like this, that B0 of 3 is like this here, right? This we have expressed like this. Same here we will express that one, that is 3 0 1 minus U to the power 3 0 U 0, right? That is 1 minus U, that is 3 minus 0 is 0 3, then U 0, that is 1, then B of 1 3 U, that is 3 1 U, that is 3 1 minus U, that is square U1, right? Then again here, if how we have derived means like this, we have used this one, we are using this and this one, right? Then here let, then B2 of 3, then this is B03, B13, B23, these are the values. Then we will substitute these in this equation, that is P of U equal to 1 minus U to the power 3 U naught, right? U to the 3, that is U raised to 0, means when U is 0, then where you are, where normally when U is 0, we are at P naught, right? Then U to the power 0, that is means U to the power 0 is 1, again at we are at P naught, then 3 1 minus U to the square V1, then U to the power 1, that is P1, then 3, then U to the power 2, then P2, then this, and P of P equal to X of P, Y of P. Then this you have to derive for XY. If it is 2D, you have to calculate this one for XY just by varying U. Means you take U first 0, then 0.2 like this. You can take 0.1, 0.3, 2, 0.3 like this, or you take one at 0, then next at 0.2, then next at 0.4, then next at 0.6 like this, means offset of 0.2, then you can calculate for X and Y, right? If it is 2D. If it is 3, then you have to calculate for all 3 like this. X of U equal to 1 just by varying U values from 0 to 1, right? 0 to 1. Then so we will calculate curve X and Y pixel by incrementing value of U by 0.001. How much approximation depends. This varying U depends on how much approximation you want, how smoother curve you want. If you want more smoother curve, then the increment factor you reduce. You reduce you take less incremental factor. If you want some approximation, then this incremental factor you take bigger value, right? Then Bezier, as I told, Bezier curve properties are the first and last control points are interpolated. First and last control points are interpolated, as I told. Interpolation in sense means that curve must pass through the control points. That curve must pass through the control points. That's why by default first and last control points our curve must pass. There is condition that the first and last points our curve must pass, cover, right? Remaining it may approximate. That is the one first property, right? The tangent to the curve at the first control point is along the line joining the first and second control point. The tangent to the curve at the first control point is along the line joining the first and second control point. Means always the tangent means the vector is from point 1 to point 0 to point 1, right? That is the meaning. Then the tangent at the last control point is along the line joining the second last and last control point. The tangent at the last control point is along the line joining the second last and the last control points, because we are not calculating the tangent at first and last normally. That's why by default the tangent at first is towards the second, then tangent at last but second is towards the last point, right? No need to calculate tangent at those points because those are covered by our curve. The curve lies entirely within the convex hull of its control points. The curve lies entirely within convex hull of control points means like this. Convex hull of control points means if you draw, this is convex hull, whatever dotted line we have drawn, P0, P1, P2. If you draw this is the convex hull. Always the curve lies within that convex hull. Again here also if I draw like this, P0 to P1, P1 to P2, P2 to P3, then P3 to P0. If I draw convex hull, always the curve lies within that convex hull. Anywhere you take. If I draw P0, P1, P1, P3, P3, P2, P3, P0, then always this lies within this convex hull. That is the meaning of that, right? Convex hull of its control points. They can be rendered in many ways. They can be rendered many ways. As I told, same control rendered many ways, right? If I take this like this, it will be like this, right? You can render any order, right? Then the degree of the polynomial defining the curve segment is 1 less than the number of defining polygon points. As I told, the control point degree is always 1 less than the number of control points. Therefore, for a 4 control points, the degree of the polynomial is 3. That is cubic polynomial. Right? Then by using this concept, we have drawn the one program. We have executed one program, that is flat. That is ninth program. Ninth program is implemented by using Bezier curve concept. Right? This is regarding Bezier curve. This completes the computer graphics and visualization subject for 6th semester. Thank you.